to start on time and finish on time. Hope you had a nice couple of weeks where we had one class in 2 weeks. Now I think we're going on a more regular schedule. Before I start, let me just mention that on Blackboard, I have posted the pictures of everything I wrote on the Blackboard for all the previous classes, as well as videos of every class except the first class. And that's thanks to the lady in the front row who was nice enough to video the class and to send me the links and to set up a closed YouTube site so that you need the link to get in, but I think only we can get in and nobody else, right? Well, there's no password? Okay, you might want to put a password on it so the whole world won't learn control.
I tried to put the password, but it's not really working.
Okay, so if someone else on the street wants to learn control, they can also tune in. Okay, so that's on the website. You can just link to it at any time. And of course, you can ask me questions. Again, I have office hours today at 5 at normal times if you have any questions. So why don't we start now with questions? Are there any questions about where we are, about any of the previous classes, where we're going? Somehow this is seat funny because Robert is kind of sitting in a seat. Oh, was it? Yeah, but there's no water in it. Okay. No, I thought the garbage can wanted to learn, so it was interesting. Are there any questions? Okay, so let's just review what we did last class. If you remember what we did last class, again, feel free to interrupt me at any time if you have any questions. What we did, and again, please make sure to upload your vaccine certification so that they don't kick you out of the class, which has nothing to do with me. The other thing is I have to verify the enrollment. So I'm going to do that based on the attendance today. So can someone volunteer a piece of paper and make sure and just pass it around so everyone signs it legibly so I can read it because I have to verify the enrollment. Who wants to volunteer a piece of paper? Okay. Please write your name clearly so that I can read it. I'm not good with handwriting. Not my own and not reading other people's. Okay, so if you remember what we spoke about were some generalities, the goals of control. And then we also spoke about that we need to be able to model a system and analyze the model before we can put control in a model. So we're spending the first half of the semester, pretty much, maybe even a little more, learning how to model systems mathematically and how to analyze those models. And the reason why we're spending this much time on it is because, first of all, in all your other classes, you really only learn steady-state modeling. And here, because of time dependence, we're learning unsteady modeling. And what that does is in many systems where you had algebraic equations, now there's a derivative in them. In many situations where you had derivatives with respect to space only, now you have other derivatives with respect to time, so they become partial differential equations. Now, you had an ordinary differential equations class, but you probably haven't gotten to use that a lot. So in the first couple of this week, we're going to be sort of doing a good workout in ordinary differential equations, the simplest ordinary differential equations. And what we saw last time is we're going to come across this equation so often that instead of solving it every time going through the steps to solve it, we solve it once and for all. So this is where y is the dependent variable, t is the independent variable. We have dy dt is a1 of t times y plus b1 of t. This is a linear equation because you never have more than one y in any given term. And it's first order because there's a first derivative. But the coefficient here and the inhomogeneity here can both be functions of time. If they happen to be constants, we wrote the equation this way and we just had exponentials. If, on the other hand, the a and or b are, in fact I don't need ones, just a and or b, are functions of time, then the equation gets a little more complicated because I can't do the integrals in general. I have to do them for a particular value of a and a particular value of b. And we derived this last time, maybe in a little bit too fussy of a way. Now, there are two things here that you may think this professor is being too fussy. So let me just mention what they are. First, instead of just putting t here, I put t minus t1, because t1 is the time that things start. Usually, we set that equal to 0. But as we said last hour, sometimes we do one thing at time 0, another time at t1, another change at time t2, etc. So if we do that, then the equation is from the last change. So for example, if we have an inlet and that's steady, and at time t1 we change it, and at time 2 we change it again, at time 3 we change it again. So for each region between 0 and t1, between t1 and t2, t2 and t3, it's possible that this is the solution. But each region has its own solution. So I always have to, and it always starts at the time of the last change. So that's why I fussed about putting a t1 here and a t1 here instead of just setting it equal to 0. And we're going to do an example of that right in a few minutes. I also fuss about saying, you know, A1 and A and B might be functions of time. The example we did last time, they weren't functions of time. We're going to do examples today where they are functions of time and where I need this form rather than this form. So we're going to see, and they're not contrived, wacko examples. They're going to be serious examples. They're going to be real examples, like obvious ones that come up a lot. Are there any questions on that? Yeah? Capital T. No, this is a small t. Oh, yes. This should have been, thank you. This should have been A1. Thank you. It should have been A. Thank you. A. I was thinking ahead. Okay, so let me mention why I call it T, because that was actually the next thing I wanted to say. Notice that over here, every term in an equation has to have the same units. So every term has the units of y over the units of t. So this term, there's a y here, so that says that a has units of 1 over t. So in particular, a of t is 1 over t of t, if you like. I can call it capital T. And the reason for that is because a has units of 1 over time. And what you can see is that a, which is units of 1 over time, is the time constant of the exponential in the case where things are constant. They tell you how quickly things decay. Because on the numerator you've got t minus t1, and that's multiplied by a, which is 1 over t. So clearly the exponent goes down based on how the exponential goes down based on how the exponent itself changes. So, for example, a characteristic way of measuring how quickly an exponential goes down is how it goes from 1 to 1 over e. So how it goes from 1 to 1 over e. So it goes to 1 over e when t minus t1 over a is equal to 1. So when it goes to 1 over e, over t is equal to minus 1. Or t minus t1 is equal to, let's say, is equal to plus 1, is equal to big T. So when an amount of time, this is the beginning, when an amount of time has passed, t minus t1, that's equal to big T, then the exponential has decayed from 1 to 1 over e. And this is the time t. So it has a physical meaning, a graphical meaning, and it tells you how quickly the exponent decays, and it's the time constant of our system. That's what we call it, particularly when it happens to be a constant. Well, was there another question here? I'm sorry, I saw another hand up here. So let's just recall what we did in the last hour. In the last hour, we looked at the situation where we had a CSTR with no reaction, and so we had dCA dt plus CA over tau is equal to CA in over tau, where CA in, and this is t0, went from one value to another. And we were looking to see, can we look at CA as a function of t? And we knew that CA was a constant, was actually equal to this constant, and eventually it went to this constant because there's no reaction, but we found that it didn't go as a step function, it went as an exponential. That's what we found last time. But the important thing is, based on what we're saying here we can see that A was 1 over tau, and B happened to be CA in over tau. Now, CA in this case, for t greater than 0. So that was the second one. Okay, so the important thing here is, as I just said, when A happens to be a constant, then t can be thought of as a time constant. And you can see the time constant is this tau, which we said is the space-time, where tau is the volume over the volumetric flow rate. And basically, and the reason for that is since there's no reaction going on here, the only physical time in the system is how long it takes to replace one volume's worth of fluid by virtue of the volumetric flow rate. That's the only characteristic time of the system, and we see that comes up, tau, in the solution, because A was 1 over tau, and we know that the solution has an e to the minus t minus t1 times A, which is 1 over tau. That is, it looks something, in this case, t was equal to tau. Are there any questions on that? That t was equal to tau. Questions? Okay, so now what we'd like to do is we'd like to add a complication. This is sort of like the way we do things. We start with the simplest case, and then we add one complication after another. This one isn't such a bad complication at first. So let's look at a CSTR. So now, we're going to take the same CSTR with the same tau, but we're going to add a reaction, a first-order reaction. A goes to B with rate constant K. You're familiar with what a first-order reaction is, correct? So what we have here now, when we write out the CSTR equation, let's recall the CSTR equation for constant and uniform density. So if you remember last time, we derived the CSTR equation in general, time dependent, where the density can change if I have a gaseous reaction where the moles are not conserved. Let's think of this as a liquid system where moles are conserved. So in that case, we had dCA dt was equal to an in minus out. So I had volumetric flow rate, V times CA in minus CA minus K CA V. Where I have a CSTR, where remember I have CA in here, I have CA here, but since it's well mixed, CA on the outlet is the same as everywhere in the reactor. Because it's well mixed. That's the assumption of well mixed. And we're given V, the volume of the reactor, the volumetric flow rate, the density. We're given that it's a CSTR. And we're also given C, and what we're told is that CA in, here's t is equal to 0, goes from one value to another value. And we're told that for t less than 0, the system is in steady state. Is the setup of the system clear? Yeah? I'm sorry, can you, just when you ask?
Sure. In the CSCR equation, there's a little squiggle before CAA minus CA. What is that?
Oh, no, that's a V.
Oh, the V, okay.
That's my bad handwriting. Sorry. So if we divide through by the volume, the V's cancel here, and this is just 1 over tau. And so this is given, and what we want to find is what happens in this case. So we know that I had some sort of steady state. This was steady state. This is CA. This is t is equal to 0. We want to know what happens for t greater than 0. Now, because there was a reaction in this case, this value and this value are not the same. Actually, if I should have written this a little bit lower because it's depleting. So let's see what happens. And let's keep in mind this business of time constant. Is everyone with me on what the question is? It's always good to know the question before you start trying to come up with an answer. If I give you an answer and you don't know the question, it's not going to help you. Again, stop me if there's any questions. So let's now bring all the CAs, not the CA in, but let's bring all the CAs to the left. So I have dCA dt. And notice this came in with a minus, and this came in with a minus. So I bring them to the other side of the equation, and I've got a k for this times CA. And here I have a 1 over tau. And that's equal to CA in over tau. Where all I did is I rearranged the equation. And I'm going to write this as k tau over tau. So I could bring it into one constant here. This thing is, as you can see here, it's 1 plus k tau over tau. And that's functioning as my a. So I'm going to call this thing 1 over t. Let's rewrite it. I have dCA dt is equal to plus CA over t is equal to CA in over t, over tau. And let's see what's going on here. Notice this is exactly of the same form here, but now A is 1 over t, and B is CA in over tau. This is B. And A, we said, is 1 over t. Notice the time constant, this equation looks just like this equation, except instead of there being a tau here, there's a t here. And what does that mean? That means the character, and remember, A, when we're dealing with constants, here, A is a constant and B is a constant. So I'm still in the constant situation. Here, the time constant, that we said A, which is 1 over t, is 1 over the characteristic time constant of the system. By virtue of putting in a first order reaction, K has units, notice, K has units of 1 over time. K has units of 1 over time because K tau has to be dimensionless. So tau is units of time, K is units of 1 over time. So what we can see is that we have a rate process which contributes something that has a time constant, and there's still the time constant of the flow in the system. So the time constant that governs how quickly CA changes, that time constant is t, where again, let me stress, t is tau over 1 plus k tau. So before I even solve the equation, you can see that there's a new time constant. There's a new sheriff in tau. The new time constant is tau over 1 plus k tau. And notice no matter what k is always positive. The denominator is bigger than 1. Since the denominator is bigger than 1, t is less than tau. In other words, things speed up, things change faster when I have a reaction. Duh, of course. Here, in order to wash out what I had initially, I have to wait for the flow to do it, to diminish the Ca. Here, I not only need to have the flow diminishing Ca of what I had initially, but I also have the reaction. So things go faster. And let's see how that comes out in the equations. Right now, I haven't solved anything. I've just looked at it and used the intuition that we built up from this situation here. By the way, it looks like a fair number of people are not here. You should tell your classmates that I'm verifying attendance today. And if they're not on the attendance sheet, they're not going to be verified, and then they're going to have trouble. So they better, if they're not on the list now, they better get to me before I verify attendance. Because I can only verify attendance of people who are here. Okay, so let's write out the solution of this. Well, this again is exactly of this form. So let's write out, and it's the constant case. So y is Ca, so I have Ca of t is equal to. In this particular case, we can set t1 equal to 0, because we're starting from here. So in this case, I'm going to set t1 equal to 0. So in this case, I have Ca of 0 plus times e to the minus t, because t minus t1 I'm setting equal to 0. A is 1 over big T. Plus b over a. So this is b. So I have Ca in, and now this is Ca in for t greater than 0. Because I'm looking, this is valid for t greater than 0. I'm looking for valid for t greater than 0. So it's Ca in for t greater than 0. So that's this value times Ca in over, B is Ca in over tau, divided by A. A is 1 over t. So this is divided by 1 over t. Times 1 minus e to the minus t over, e to the minus t over big T, where again, A is 1 over big T and t was equal to 0. Now let's figure out what this thing is. This thing is 1 over t divided by 1 over tau divided by 1 over t is big T over tau. Big T over tau is 1 over kt. So this whole thing is Ca in of t greater than 0 divided by 1 plus k tau. I still need to determine what Ca of 0 is. So let's just rewrite it. I want to rewrite it in a way, well, I want to rewrite it in a way that, let's leave it. Let's figure out what Ca of 0 is. To find Ca of 0, I need to look what happened before t is equal to 0. Before t is equal to 0, Ca in was Ca in of t less than 0, not Ca in of t greater than 0, and the system was at steady state. So the equations look just like this, except it was steady state, so the derivative was 0. Well, this was, so the derivative was 0. And so all I had was this, and this was Ca in for t less than 0. So I had, for t less than 0, Ca t less than 0 over t was equal to Ca in for t less than 0 over tau. Well, let's figure out what that is. That says that CA for t less than 0 divided by was equal to CA in for t less than 0 times big T over tau. Well, we just said big T over tau is 1 over k tau. 1 plus k. So let's put all that in here, and I have CA of t is equal to. And what I want to do is I don't want to have the exponential twice. So I'm going to write out the constant, and then I'm going to combine the two exponential terms. So the constant term we said was CA in for t greater than 0 divided by 1 plus k tau. Okay, so that is with the constant. And then I have minus CA in, same thing, CA in for t greater than 0 divided by 1 plus k tau times, and this term has the same exponential. So a minus is a plus. So I have CA of 0. This is CA in for t less than 0 over 1 plus k tau. And this thing is CA at t equals 0 times e to the minus t over tau. T over t. And here I have the solution. And again, notice, as we said, the time constant t is exactly the time constant that we said it would be, which is the combination of the flow and the reaction. And what does this look like? This is a constant value. And notice here I could factor out the 1 over 1 plus k tau. And I have the numerator would just be the jump in the CA in. It's this particular jump. So, So notice this is a constant plus minus a jump times an exponential. So it's an exponential decay. And what happens? So I could have, and we'll calculate in 1 second. I'm going to have an exponential decay. And what is the value as t goes to infinity? As t goes, what happens as t goes to infinity? CA as t goes to infinity. Well, as t goes to infinity, this thing goes to 0. And I just get this first term, CA in of t greater than 0 over 1 plus k tau. So this thing, the final value here, is CA as t goes to infinity. And this was CA steady state for t less than 0. And I have an exponential decay between them. So the new value as a function of time is the infinite, the steady state solution, plus the jump over 1 plus k tau times an exponential decay. And what you can see is, again, with the constant coefficients, we just get exponential decays. And that's what you expect from first order systems. First order systems give you exponentials. But the exponentials get a little more complicated as if we try to do things, some other things. Any questions so far before I put some numbers in? Now I want you to notice CA as t goes to infinity is the steady state after the jump. And notice it's exactly the same form as the steady state. This is a steady state value. Before the jump. But before the jump, it was based on CA in for t less than 0, this value. And after the jump at infinity, it's based on CA in for t greater than 0. It's based on this value. But it's the same form because it's the same tau, same flow rate, same reactor, and the same reaction. So it makes sense that it's the same form, but it shifts from one value to another based on these two. Okay, any questions? Yes?
How did we determine that CA of t equals 0 is that?
I'm Sorry, how do I determine?
That CA of t equals 0 is the...
This is t less than, t greater than 0, and t less than 0.
And underneath it, you put CA equals t of t equals 0.
Okay, no, that's just what this value is. Because if you remember, I had CA of 0 here. CA at the change. And CA at the change, we say CA of 0, we're given, because of this, is equal to CA steady state for t less than 0. We're given that here. So I call it CA of 0, but we know from the given that that's equal to the steady state value for t less than 0. If I set up the problem differently, it would have had to have been that. Okay? Questions? Okay, let's make this more of a problem with numbers. Not that I'm going to do any numerical calculations here. They give you numbers in the book. They give you k a certain value, and they give a certain value for tau, another value. And so then they calculate, for example, you calculate CA at t less than 0. That is the steady state value. If you know k and tau, you can calculate, and you're given CA in t less than 0. These are all given. I think this is given as 0.903 or something, 0.9 something, and 1 over 1 plus k tau turns out to be 0.503. And what is the other thing? 0.925. Yeah, I can write a lot bigger. Sure, sorry. Okay, sure. So they give you numbers here for it. And they tell you, in this particular problem, that, let's see, what are they doing? Let's see what the problem is here. Yeah, they double it. So CA for t less than 0 is a half of this, and CA for t greater than 0 is 0.925. So what they do is they go from value to 0.925. So these are just numbers in the textbook. But what I want to make the question is, actually, in this case, if I'm raising this, then I should be raising this. Okay, so what they tell you is, obviously, if I'm raising the input, I'll be raising the output. And what they tell you is, it's dangerous if CA goes greater than or equal to 0.85. So what they do is they put an alarm when CA is 0.83. So the question is, how do I calculate how much time it's going to take for the alarm to go off? How do I know how much time it's going to take for the alarm to go off? So I can set CA equal to 0.83 or 0.85, whichever of both of them. Everything here is known. 1 plus k tau CA in is known. I know CA in for t greater than 0. So this is a number. I know 1 plus k tau. I know CA in t greater than 0 and less than 0. This is a number. So I have a known number times e to the minus t over a known number. So all I have to do is subtract this. So I set this thing equal to 0.83. Subtract this. Divide by this. Take the log, and that's equal to minus t over little t over big T. So hopefully I don't have to go through the details of that. And you can calculate little t of CA is 0.83, and little t of CA is 0.85. And what you find is, if you let it go forever, this value will be greater than 0.85. That's why they chose these numbers. So that says, wait a second, there's an alarm. Okay, so what happens here? Let's imagine. So here so here's t is equal to 0. And let's say if I let this go forever, this will reach a value that's greater than 0.85. But let's say 0.85 is somewhere around here. And 0.83 is just a little bit below it. If I don't do anything when the alarm goes off, I'm going to exceed 0.85. So what would you do? What do you think you should do to make sure you don't go over 0.85 and cause a problem? Maybe destroy the equipment. What would you do? I'm sorry, can you just put your mouth? Stop the supply, lower the concentration. So what you might do is, so here is CA out versus T, and here is CA in. So we said at time T is equal to 0, we went from here to here, and we went from a certain value, and it's trying to get to here, but we don't want to exceed 0.83. We don't exceed 0.85. So let's say here it's 0.83. So what that says is if I want to avoid the danger zone, then at this particular time, maybe I should go back to the old feed. And if I do that and have a different colored chalk, then beyond here, instead of this continuing to go up, this will now start to decay back to the old steady state because I went back to the old feed. So I keep it from going any higher. So notice, even though this was at T0, this happens at a new time, T1. And that's why I need that particular solution. And so let's see from what we have here, if we know what that solution is, the blue solution. So the blue solution would be CA of T for T greater than T1. Is this big enough, or is this still too small? Well, so this was CA in, now it's T greater than T1. So this is for CA for T greater than T1. Divided by 1 plus K tau. And that we know because for T greater than, well, again, this is the form of the steady state based on the new feed. Plus, a minus. Well, here again, I have the same thing. CA in of T greater than T1 divided by 1 plus K tau. But now I have CA at T is equal to when the switch happened. In the new version, this is at T is equal to T1. At T is equal to T1, CA was not steady state. It was steady state at T is equal to 0. So that's why I left it this way. Here I have to subtract CA at T1. The value of CA where I made the switch. That's what this was. That's why I left it here. Remember, that was this value right here. And now that's multiplied by e to the minus t over big T. But this is not t, this is t minus t1 over big T. So all of a sudden, because I did something at a time different from 0, I say, I'm glad I kept the T1 here. Otherwise, I would have had to have derived it from scratch. Is that clear? So I basically went back to this equation and remembered where there should have been T1s. There should have been a T1 here, so that's here. And there should have been a T1 up to the exponential. That's why I have a T1 here and a T1 here. So I don't have to do the work again. I've done it. And this is valid for T greater than T1. And we see what happens is we get this exponential decay, And how do we know? Well, let's notice as t goes to infinity, t minus t1 goes to infinity, this dies out. This is an exponential. And we're just left with CA in for t greater than t1 over 1 plus k tau, the steady state solution, which since I happen to have chosen CA for t greater than t1, the same as CA in for TA less than 0, I get the same value I had before. Had I chosen a different value here, the numerator would have been different from this numerator. Are there any questions on that? So, what we've shown here is it's a good idea that we kept the T1 here and it was worth fussing to keep the T1. For some reason, your book doesn't really make an issue of that. And I find that's a thing that can be very confusing unless one stresses that explicitly. When you keep the T1, when you have a situation like this, where you do multiple changes, you have one equation in this region, another, and that's this equation. You have another equation in this region. That's this equation. Remember, this is true for t greater than 0, less than t1. Once I make the change, I have another equation in this regime, because I made a change. Things have changed, and that's this equation. So we have to recall, every time I make a change, there's a new equation. Now, if I have a continuous change, rather than a step change, then I have to solve the whole problem at once, where b of t is a function of time. And we're going to do an example of that too. But when I have step changes, I have a separate equation in each regime. Are there any questions? Yeah?
Could you have made the concentration anywhere from where you started to where you are now? Why bring CA back to the original?
Oh, just because that's what they do in the book. I could have done any value. What I really wanted to do is do any lower value so this doesn't continue to go up. I want to make sure that it's just any lower value. And in fact, there isn't anything that would change here other than the picture. So for example, if I chose a value even lower, then this is CA in at t greater than t1. This would just be small lower value. The equation will be the same, but the picture would look a little different. Instead of being where it is now, it would be down there, and this would have decayed to the lower value. But the equation would look exactly the same, because all I'm doing is changing the value here. Sure, no, thanks for the question. Other questions? All right, well, let's make life a little more complicated. Not because we want to make life more complicated, but because life is complicated. Let's imagine that we have the same problem we had before. I'm not going to worry about the numbers here. But instead of one CSTR, we have two CSTRs in series. We'll call this CSTR1 and this CSTR2. We'll call this CA in. We'll call this CA1, and we'll call this CA2. Now, we've already solved for CA1. We know what CA1 is. It's just what we had here. This is CA1. Here it is. But now we need to solve for CA2. Let's write the equation for CA2. Well, here I have the general equation. Now for dCA2 dt, let's just copy it over. dCA2 dt is equal to 1 over tau something minus CA2 minus KCA2. But and notice what I have here is CA in. Now, if I'm looking at reactor 2, what's coming into reactor 2? CA1 is coming into reactor 2. So this is CA1 for t greater than 0. But CA, whereas what was coming into reactor 1 was a step function, what comes out is an exponential. So CA1 is a function of time. It's not a step function anymore. It's this guy. So let's rearrange it. I have dCA2 dt is equal to, and let's allow tau 2 to be different from tau 1. Maybe they have different volumes. If they have different volumes. So now I have 1 over tau 2. Well, let's bring this to the other side of the equation. I've got k plus 1 over tau 2 is, so CA2 over T2 is equal to CA1 of T divided by tau 2, where T2 is tau 2 over 1 plus k tau 2. So all of a sudden this equation has, even though A of T, A2 of T, A2, say A2, is equal to 1 over P2. That's a constant. But B2 is now a function of time. It's CA1 of T divided by tau 2. So luckily, we also came up with the general solution for the case where we also came up with the general solution where B is a function of T. A is not a function, I'm sorry, which one is, A is not a function of time, but B is a function of time. So I'm sorry I'm running back and forth, it makes, you have to work with the camera. I've got questions, because I want to get the issue clear before I actually get the solution. Can you just, when you ask the question? Yeah, they're the A and the B from this equation, but since I have a reactor 1 and reactor 2, there's an A and a B for reactor 1 and an A and a B for reactor 2, so I gave them subscripts. So I've just written A2 and B2 are the A and B in this reaction, but for in this equation, but for reactor 2, because this is the equation for reactor 2.
No, but I'm saying you substitute for A and B just for simplistic reasons, just so.
Oh, I substituted, I just reminded you what A and B are in this equation, because I'm going to appeal to the solution that has an A and a B in it. Is that clear?
Is that supposed to be CA1 of T greater than 0? Or just CA1 of T?
C at T greater than 0. Well, the whole problem is from T greater than 0. So this, I'm looking for a solution valid for for T greater than 0. So here I'm just being fussy, and I'm telling you I'm looking for the value for T greater than 0. Now, of course, again, we know the system was at steady state for T less than 0. So we know, so recall, CA1 for T less than or equal to 0 was equal to CA in for T less than 0 divided by 1 plus K tau 1. That we know. That's exactly what we had here. I had it somewhere. CA in here. That was no. Let's calculate CA2 for T less than or equal to 0. What happens to CA2 for T less than or equal to 0? Well, we can do that again directly from here. At time less than 0, the whole system was at steady state. So if the whole system was at steady state, dCA2 dt was 0. So that tells me that CA2 steady state was T2 over tau 2 CA1 at steady state. Clear? Because the same equation held, I just had CA1 for T less than 0. T2 over tau 2 is 1 over 1 plus K2 tau 2. So this says CA is CA2 steady state t less than 0. And that's equal to, we said, that's equal to CA1 steady state. And I should write it a little bigger, so I'm looking for t greater than 0. So now I have CA2 steady state. That's equal to CA1 steady state, which is this. CA1 steady state, that's steady state, times T2 over tau 2. T2 over tau 2 is 1 over 1 plus K tau 2. So before I even solve the unsteady problem, the steady solution, that is what was happening before t is equal to 0, I know that. So let's just keep track of some graphs. Some of them will be reruns. This is t. Here's 0, 0, 0. This is CA in. CA in. This is CA1. And this is CA2. And we already know the first two. The first two, I go from here to here. Step change. We know CA1. Just going to copy it from there. We go from here as an exponential k to some steady state. So the question is, what happens here? Obviously, I was at some value here. Here it is. So this value is this value. This value is that value. And the question is, what happens here? Is that clear what the question is? All right, is it clear what the question is? Again, make sure those who came late that you sign, that you legibly write your name on the attendance sheet, because I have to verify enrollment today. I should have done it a week ago, but with all the days off, it didn't happen. Okay, and for those who came in late, this student has been kindly recording the sessions. So the links to each of the recordings are on Blackboard. If there's anything you missed, if you're having trouble sleeping late at night and you need a recording to put you to sleep, you can watch the lecture again. Okay, so let's go ahead and do it. We know what A2 and B2 are. So let's notice all over the place we've got the integrals of A dt. Since A is a constant, this just becomes e to the minus A t minus, and in this case, we're going to set t1 equals to 0. So here we're going to set t1 to 0 because we're starting at 0. And let's notice that e to the minus integral a of t prime dt prime from, say, t1 to t, I know what that is for a2. Because A2 is just a constant, so I can pull it out, and T1 is 0. So in this case, this is just e to the minus A2 times T. So wherever I see this guy, in this particular case, because T1 is 0, and because A is a constant, I can make life easier and just make it an exponential. So let's plug in and do it. So I have CA2 of t is equal to something. Well, sorry, I got to run back and forth here, so I'm getting my exercise. CA and T1. So CA2, this is the initial condition. T1 is 0. Y is CA2. So it's CA2 and T1. CA2 and T1 is CA2 at 0, which is this. T less than or equal to 0. So instead of writing it a million times, let's just write it now CA2 at t less than 0. At the end, I'll plug in for it, but I want to minimize the writing after I do the manipulations. That's times the exponential, e to the minus a2t. plus e to the minus a2t. And I'll plug in for a2 later. Actually, a2 I can plug in for right away. That's just t over t2. Times an integral. And I'm integrating e to the plus a2t. Times b dt. B, and this is a t prime, and this goes from 0 to t. And I need b. So what's b? B is CA of T1 over tau 2. So let's bring the tau 2 out. And I have CA of T. CA of T. What's CA of T? Well, I know what CA of T is. Here it is. It's CA, again, to make the simplify the writing, this is CA steady state of T greater than 0. Just so I keep the writing a little easier. So CA steady state of T greater than 0. And here I have the same thing. So I have CA steady state T greater than 0 minus CA at T equals to 0. This is CA1. Minus CA1 at T less than 0. Times e to the minus, actually I have the exponential there. No, here's another exponential. E to the minus T over T1. Because that was from T1. Okay, before I go any further, I want to make sure you understand what I just did. So what did I do? I used the fact, let's again review. I used the fact that this equation has CA1 as a function of t. So b is a function of time, a is not. I appealed to this equation. Why is CA2? CA2 of t is CA2 of T1. T1 is 0. So it's the initial value. That's CA2 steady state. CA2 steady state, or CA2 of t less than 0. Times the exponential. We said e to the minus a dt, that integral, was just equal to e to the minus a t, e to the minus a t over here. And then I went to the next term, I got the e to the minus a t. So I had e to the minus a t on the outside. And on the inside, I had e to the plus at times c times b of t, dt prime. So here I've got a t prime, I've got the t prime, dt prime. And this whole thing is CA of T1. CA of T1 I got directly from here. I just needed to note that the CA is all CA, this was a CA1 and this was a CA1. But I have e to the minus t, and this had to be a T1 because of the solution to T1. Are there any questions on that? Questions? I went through it twice, so I hope it's clear. All I did was I plugged into this equation where everything that refers to what happened at t equals 0 was the one solution. Similarly, the input was the one solution. Okay. So now I can go and do the integral. So this gives me, this is CA2 at t less than 0 times e minus e over t2 plus. Well, let's do the easy one first. That's this one. Because here I have another exponential. Let's do the simple one first. So the next term is I have a CA1 steady state for t greater than 0. That's this. CA1 steady state for t greater than 0. And now I'm integrating I have 1 over tau 2. And now I integrate the exponential. I just integrate an exponential. The integral of e to the t over t2 is 1 over t2 e to the t over t2. It's 1 over 1 over t2. So that's, I divide by the coefficient, which means I multiply by t2. Or if you like, I divide by 1 over t2. Times the exponential at the numerator minus the exponential at 0. So here I've got e to the minus t over t2. That came on the outside. And then here I get e to the t over t2 minus 1. So this I came along for the ride, and the tau 2. The CA1 steady state was a constant that came along for the ride. And when I integrate this, I just get the exponential back divided by the coefficient. And the exponential back at t is this, and at 0 is that. Is that clear? Now I have to do the next term. And the next term is, so I'll write next term. So I can go to the top of the board. So I have CA of t is equal to, it's equal to CA t less than 0 times e to the minus t over t2 plus CA1 steady state t greater than 0. Now let's look at what tau 2 over t2 is. Tau 2 over t2 is just 1 plus k tau 2. Tau 2 over t2 is 1 plus k tau 2. So this is 1 plus k tau 2. And when I bring the exponential in, this could be 1 minus the negative exponential. Is that clear? And now I get to do next term. So let's look at the next term. The next term, I have plus. Is it plus or minus? Minus. Well, minus and minus is plus. No, minus. So I have minus CA1 steady state for t less t greater than 0. Minus CA1 for t less than 0. All of that times an integral. So times an integral. Times the integral from 0 to t of e to the t prime times 1 over t2 minus 1 over t1. dt prime. Is that clear? I just did this term. This comes along for the ride. And I probably left out some factors. I need to multiply by this over this, because that's on the outside. So I have, let's give myself a little room here, minus e to the minus t over t2 divided by tau 2. So this last term was e to the minus t over t2 over tau 2 times this coefficient, came in with the minus this coefficient, times what's left? An exponential with a 1 over t, 1, 2, and an exponential with a 1 over t1, t. Is that clear? Yes? No? Yes? Which point do you want me to start at? From here?
Yes, that would be great.
Okay. Sure. That's what I'm here for. Okay, so I'm appealing because this equation has B as a not constant. So I'm appealing to this solution. Okay? And where T1 is 0, because the change is happening at 0, so T1 is 0, and the variable is CA2. I'm interested in this variable. So I have CA2 of T is CA2 at 0 times an exponential. So it's CA2 of 0 less than or equal to 0 times the exponential. So the exponential was just A was 1 over T2. So I had e to the minus T over T2. And then the next, because I have the minus sign here. And I have the same factor here, e to the minus T over T2, e to the minus T over T2, times the integral of B times e to the plus exponential dt. So I need an e to the plus exponential in here, and now I need to plug in B. So B, we said, B is just CA1 of T over tau. So the tau comes in, and the CA1 of T is this guy. So I have the constant plus the difference of two terms times an exponential. The constant plus the difference of two terms times the exponential. But because this is CA1, this is a T1, and these are CA1. This is a T1, and these are tau 1s. But I didn't, so I wrote it this way. The main thing is I've got a T1 up here. So now I have to go through and do the integral. The first term I just copied. The next term, I copy this, just copy that, and this is a constant, I copy that. So that's this, the exponential over this. So those are the coefficients. And now I integrate this. When I integrate an exponential, I just divide by the coefficient of the t. So I divide by 1 over t2. And I get the exponential back. At t, I get this. At 0, I get this. And then plus the other term, which I postponed. So I just copy this over. This I copied here. This term I copied here, where I noted that tau 2 over t2, tau 2 over t2, which is 1 plus k tau 2. And I multiply this in. So I got 1 minus an exponential. And now all I'm doing is copying over the integral that I still need to do. So I've got a minus sign. So minus sign came. The exponential and a tau 2, here it is. The difference of constants, there they are. And what's left in the integral? Inside the integral, the only thing left is this guy, and dt time. So that's one over, since they're multiplied, I just get this.
What's T prime?
Dummy variable. That is, I can't have the same variable of the integration as the limit. So I make this a dummy variable that gets integrated out and just left with t. Okay. So this thing, I'm going to call this thing for a moment the integral I. And I call that just for two situations. There's I if in the case where tau 2 is equal to tau 1. Tau 2 is tau 1 means, well, why don't I go back even further? V2 is V1. If V2 happens to equal to V1, did you have a question? That's right. If V2 is equal to V1, remember we said volumetric flow rate is a volumetric flow rate. If V2 is equal to V1, then tau 2 is equal to tau 1. So if V2 is equal to V1, then tau 2 is equal to tau 1. But if tau 2 is equal to tau 1, T2 is equal to T1. So what happens to I in that particular case? Well, notice if T2 is equal to T1, 1 over T2 is equal to 1 over T1, and this just becomes the exponent is 0. So I'm just integrating 1. And then I is just equal to T. So in the special case where T1 and T2 are the same, I just becomes T. But in the case where T2, V2 is not equal to V1, which tells me that T2 is not equal to T1, then I need to do that integral. And what does that integral give me? That integral gives me, again, it's the integral of an exponential. So when I integrate an exponential, I just get, well, I divide by the coefficient. Divide by the coefficient, and I just get the exponential back. So I get e to the t at the upper limit, 1 over t2 minus 1 over t1, minus at 0, which is just a 1. And now I'm ready to write the full solution. Are we ready for all this writing? Am I doing it on time? Getting there. Okay, so let's write out the complete solution. The complete solution is CA of t is equal to CA of t less than 0, CA, this should be CA2. CA2 of t less than 0, which is CA in t less than 0 over 1 plus k tau 1, 1 plus k tau 2. And this whole thing we know is just, we said, this thing is CA2 for t less than 0. Times e to the minus t over t2. Where we know what t2 is this.
Why is CA2 t less than 0?
With your mask on, I can't understand what you're saying.
No, it's CA2 t less than 0, right?
CA2 for t greater than, CA in for t less than 0. This is CA2 for t less than 0. I just plugged in for what this was. CA2 for t less than 0, I noted that it was equal to this thing. Okay? So now I have CA1 steady state for t greater than 0. CA1 steady state for t less than 0, t greater than 0. CA1 steady state for t greater than 0 is equal to this guy. CA in for t greater than 0. Divided by 1 plus k tau 1. That's CA in, CA1 steady state for t greater than 0. And that thing is multiplied by 1 over 1 plus k tau 2. Here. And that's multiplied by 1 minus e to the minus t over t. So what I'm doing is I'm plugging in for all the stuff I didn't want to write 1,000 times. Since I'm at the final solution, I'm plugging everything in. Now I have this thing. So now I have the minus. Well, I've got a 1 over tau 2. I've got a CA1 steady state for t greater than 0. That's this guy. CA in t greater than 0 divided by 1 plus k tau 1. Minus CA1 for t less than 0. CA1 for t less than 0 is CA in at t less than 0. Divided by 1 plus k tau 1. That's this thing. And now I need two cases. So the first case is this one. So in this case, the exponential just gives me a t. So here I have t e to the minus t over t2. And this is I'll call this I0 and I not equal to 0. This is I0. Actually, I don't have to do that. I can just say V1 equals V2. So that way I don't need that. And otherwise, I have this being what I calculated here. So otherwise, I get 1 over t2 minus 1 over t1 times e to the something minus 1. But remember, this thing gets multiplied by e to the minus t over t2. So this gives me e to the minus, well, e to the, so e to the minus t over t2 times this is just 1 minus e to the actually, let's do one thing at a time. So when I multiply by e to the minus t over t2, this drops out. So I have e to the minus t over t1 minus e to the minus t over t2. And let's see what that solution looks like. So here I have the solution. And this is, of course, for the case v1 not equal to v2. All right, so let's look at the solution. Notice that in the previous case, over here, when I was only looking at CA1, I had one exponential. That's easy. I had a constant plus a constant times an exponential. I get a simple exponential. Here it's an exponential key to a higher value. Here, I've got two different exponentials. I've got something that's changing with a time constant t2. This is the easy part. This kind of resembled what I had for the first reactor, just going on in the second reactor. But then I have the part that comes from the time dependence of the output of the first reactor that comes into the second reactor. And that's going to have a mixture of the time constant T1 and the time constant T2, because they're different. Now, if they happen to be the same, then there's only one big T. T1, big T1 equals the big T2. But I get a power of T times the exponential. On the other hand, in the normal case where they're not exactly the same volume, I get an exponential in T1 and an exponential in T2. And what you find here when you plug in is that this ends up decaying in a different way. And if you calculate, which I'm running out of time, the derivative, you calculate the derivative dCA2 dt, and you can do this one for homework, at t is equal to 0, you find this is 0. Why is that? It's 0, and that's very physical. Why is that 0? When CA in changes in a step change, because this is very well mixed, the instant I change this value, I change everything in here. And what happens? The concentration coming out starts to change. But initially, it's still 0. Only the derivative changes. Here, the value of the function changed. But here, the function didn't change, but its derivative changed from 0 to a non-zero value. Here, so that tells me that at t is equal to 0, what's coming into reactor 2 out of reactor 1 hasn't changed yet. It hasn't changed yet. So why should reactor 2 change if what's coming into reactor 2 hasn't changed? It's the first derivative changed here, and that first derivative of CA1 changed, and that changes the next higher derivative of CA2. CA2, it's the second derivative that changes. So every reactor down the road pushes the change to one derivative higher. Now, there's something interesting about this, which I'm not going to fuss too much about because I'm running out of time. This is called resonance, which you may have had, and it's not too critical here, but it will be critical later in the semester. In freshman physics, you all had the case of simple harmonic motion, correct? So you all had the case, remember when we were kids and our parents used to push us on the swings? Now, if there were no friction, no air resistance, we would just swing forever with no one pushing us. Now, when we were kids, we didn't like to be in a low amplitude oscillation. At least when I was a kid, I liked to be really a high amplitude oscillation. How did we get to a high amplitude oscillation? Well, if some idiot came and pushed you at the wrong time, amplitude didn't go up. But if your mom came in, or your dad, and pushed you at exactly the right time, so the time constant of pushing was the same as the time constant of your natural swinging. The time constant of pushing is T1 here, because that's what's pushing what's going on here. So if capital T1, the time constant of pushing you on the swings, is the same as T2, the time constant of you swinging, all of a sudden your amplitude gets bigger. Now, that's the case if the solution is oscillatory, then the amplitude gets bigger. Here, the base solution was an exponential to k, but you have the same thing going on here. Instead of just having an exponential to k, you're multiplying by an amplitude that's getting bigger with t. This happens to decay exponentially, so this wins. But whereas, if I plot an exponential, it looks like this. If I plot t e to the minus at, it looks like this. So the shape of the curve looks different if I have a t e to the minus at. And that's the resonant case, which is not all that, as I said, it's not all that exciting when I have an exponential here. But later on in the semester, we'll do exactly the case of the swings, where I have an oscillatory solution that's multiplied by t, and then the amplitude just gets bigger. And if the amplitude, if the variable of interest is the control variable, and its amplitude's getting bigger, that's no good. Coming attractions. Are there any questions? Okay, I went 5 minutes over, but we also started 5 minutes late. So please come on time and we'll finish on time. Are there any questions? I have, again, I have office hours today.